Swayam Prabha. Digital India. Educated India.
In the last lecture, we continued our discussion of particle adhesion forces. Previously, we had looked at van der Waals forces of adhesion. In the last lecture, we looked at electrostatic forces of adhesion between particles and between a particle and a surface. Looked at the electronic double layer force that results from contact potential. Also looked at the ionic double layer forces that apply for particles that are suspended in solutions, where the zeta potential is what drives the forces of attraction and repulsion. And finally, we discussed surface tension based forces as well as hydrophobic hydrophilic forces. Since we have so many different adhesion forces that can prevail at any time, it is important for us to be able to measure the adhesion force in order to validate some of our theories on particle adhesion and also obtain data that are practically useful to us. Now, when we talk about measurement of particle adhesion forces, two ways you can do it. One is at a single particle level and the other is for a population of particles that may be decorating a surface, for example. So, our techniques for adhesion force measurement will clearly be different for the two cases. When we need to examine single particle adhesion forces, the first requirement is that we have to be able to visualize that single particle. We have to be able to zoom in on a particle and characterize what force is required to make it move. A way to look at adhesion force is that it is equal to the first removal force that is able to dislodge the particle from the surface. Therefore, essentially, instead of trying to measure the actual force of adhesion between the surface and the particle, or between two particles, or between two surfaces, instead what we try to measure is what is the minimum force that is required to overcome this force of adhesion, because you have to have perfect balance between the removal force and the adhesion force in order to reach that quasi steady state where the particle is essentially just bouncing on the surface. So that if the removal force even slightly exceeds the adhesion force, it will immediately dislodge the particle. So that gives us a convenient way of measuring particle adhesion force, because the force of removal is something that we can quantify fairly precisely. And so without having to do molecular level measurements of forces that are binding two surfaces together, we can more conveniently measure the force that's required to drive them apart and thereby estimate the force of adhesion. Now, in order to do this, you still have to develop a system in which the particle adhesion process itself can be controlled and simulated in a reproducible manner. In other words, you have to have a way of causing a particle to adhere to a surface in a manner which is very predictable. The force of adhesion should be something that is repeatable and reproducible for multiple experiments. And similarly, the force that you apply to remove the particle from the surface, you must also be able to apply it in a very repeatable and reproducible manner. In order to achieve both of them, you have to really develop a set of requirements that the surface as well as the entire system must satisfy in order to quantify particle adhesion forces reasonably precisely. Some of the minimum requirements for such a system are the following. The first thing is you need to be able to produce particles of well defined geometry. As we have seen before, the shape of a particle has a distinct influence on its adhesion characteristics. So, in order to characterize the adhesion force of a set of particles to a surface, you need to have reasonably good control over the shapes of the particle that are contained in the population. If you have a wide variety of shapes present in the particle population, then the distribution in the corresponding adhesion forces is going to be so much that you are never going to be able to really characterize a uniform adhesion force for that entire set of particles. So, well defined geometry is important, and usually spherical particles are chosen because it is more convenient to obtain spherical particles, and also the adhesion between a spherical particle and a surface does not depend on the direction of approach or the angle of approach. Whereas if you have a particle that is elliptical, for example, you can easily imagine that depending on whether the particle approaches surface end on or side on, the adhesion forces are going to be very different. So, some of those variables can be eliminated by using spherical particles as your test particles. The second requirement is that the deposition surface, the surface on which you are going to study the adhesion characteristics, must be very smooth. Again, the reason for this is that, as we have seen before, surface roughness can have a significant influence on adhesion characteristics. So, you really have two choices. A, you start with a highly polished surface so that you eliminate surface asperities as a variable, or you try to produce very controlled surface distributions of roughness in order that you can study the effect of surface roughness on particle adhesion. But in general, to study adhesion characteristics of a particle to surface, it is preferable to start with a highly polished and smooth surface so that you can eliminate the surface roughness as one of the variables. The third requirement is that all process conditions must be tightly controlled. What we mean by that is that once you have prepared the particles and you have prepared the surface on which you are going to study the adhesion characteristic, you still have to deposit the particle on the surface in order for the adhesion to happen, and you can then study the force of adhesion. Now, you will be using some transport mechanism in order to convey the particles from the source to the surface on which you are going to study their adhesion characteristics. That transport mechanism or process must again be very tightly controlled, cannot be allowed to vary from run to run. So, your flow paths that convey the particle to the surface must be maintained the same. The flow velocities must be maintained the same. If you have designed the system to have no thermal gradients, then you have to ensure that all experiments are done in the absence of thermal gradients. So, all these process conditions that can affect the delivery of the particle to the surface and the adhesion of the particle to the surface must be tightly controlled. The fourth requirement is that measurements must be quantitative but supplemented by qualitative characterization. As you can imagine, the simplest way to study particle adhesion forces would be to deposit a known number of particles of a known size distribution on a surface, count the number of particles on the surface, apply a certain force, see how many particles are removed, keep increasing the force until all particles are removed from the surface. Now, that is essentially a quantitative method. What you are really doing is, for every application of force, you are counting the particles before and after, and the removal efficiency of the particles and the corresponding force that has been applied gives you an indicator of what is the adhesion force binding the particle to the surface. But sometimes you can fool yourself if you just look at quantitative data, because there can be many artifacts when you are doing purely quantitative analysis, because what you may be counting as a particle on a surface may actually be a defect on the surface. Simple dimple on the surface you may be counting as a particle. So sometimes it is important to not rely entirely on quantitative measurements, but actually do some analysis. Make sure that what you are counting as a particle is really a particle and not just a feature of the surface or material that is part of the surface which has broken off, or a simple hole in the surface, because all of these can fool a particle size analyzer or even a particle counter into thinking that these are particles. So it is very important to be open to doing auxiliary measurements that can confirm your quantitative data. What are some of the other requirements? You have to be able to deposit known number of particles of known particle size distribution on a clean surface. So before you even begin your measurements, you have to ensure that the surface on which you are doing the adhesion test is very well cleaned, preferably to monolayer levels of surface films and particles and so on, because any contaminants or impurities that are present on the surface will interfere with your measurements and give you spurious data. So it is very important to start with a very clean surface. For example, if you are conducting experiments on silicon wafers, you have to ensure that the silicon wafer is chemically cleaned and etched so that it is perfectly clean before you start the experiment. And then you have to deposit a known number of particles of known size distribution. Now that is not easy to accomplish, because it requires a supply of particles of a known size and known count, and as we saw earlier when we were discussing particle counters, there are certain materials like polystyrene latex which can be prepared in such a way. You can either get monodispersed materials, or you can even get polydispersed materials of PSL. But even if you have the supply, how do you again transport it and put it on the surface in a repeatable manner every time? Because as you can imagine, as particles become smaller and smaller, their motion can become more and more difficult to control. So you have to have fairly good flow system designs in order to be able to deposit the same number and size distributions of particles on the surface every time. And in fact, there are specialized equipment that have been manufactured for this purpose, which are essentially aerosol deposition chambers. So these are specially designed and fabricated to ensure that particles are generated at a particular source and then they are transported and deposited on substrates that are mounted in the chamber in an extremely repeatable and reproducible manner. So typically they would look like this, with a substrate being mounted at the bottom, and there will be an inlet at the top where the particles that you are actually planning to deposit on the wafer are introduced. The generation of these particles can actually be done in two ways. The particles can be generated externally and introduced into the chamber as a fine distribution of particles along with some carrier gas or carrier fluid. The other way is to actually generate the particles here inside the chamber. Again, in terms of control over the process, the latter is actually preferable. You actually want the particles or droplets to be nucleated within the chamber. Now, there are again specialized techniques to be able to do that. Nebulizers are used for this purpose. Vibratory orifices. Essentially, the way these work, if you take a continuous film of liquid and you pass it through either a vibratory screen or a nebulizer typically uses an ultrasonic horn, they make the film vibrate at very high frequencies. As they do, the film breaks up into fine droplets. In the case of a nebulizer, by changing the frequency of the ultrasound, you can change the size distribution of the droplets that you generate. And similarly, in a vibratory orifice, by changing the vibration frequency, you can generate droplets of the size that you are looking for. Typically, the nebulizers are used to get finer particles compared to vibratory techniques, which are used to get coarser materials. Now, in these chambers, what they do is they pay a lot of attention to how these particles are then transported to the wafer on which you are trying to deposit them. So, the flow will be designed so that it's laminar and it follows the same path every time, so that there is no intermixing of the streamlines, there is no turbulence, there is no recirculation, there is no stagnation, because it is very important that we establish a stable flow in this chamber and we convey the same number and size distribution of particles every time to this substrate. Now, streamlines are good for transporting particles that are in an intermediate size range, which follow the streamlines. But as we know, particles that are much larger will not follow streamlines. They will inertially impact if the Stokes number is high enough. And similarly, particles that are very, very fine will not follow the streamlines either, because they will essentially follow diffusional paths, so they are very likely to deviate from the streamlines. So, this strategy of using essentially a unidirectional laminar flow works well for particles that are roughly in the 0.1 to 10 micron size range. But for particles that are smaller than 0.1 microns or larger than 1 micron, simply relying on flow streamlines is not sufficient. So, you have to control not only the flow streamlines in those cases, but anything in the design of the chamber that can affect diffusional paths. For example, when you talk about diffusion, even slight temperature non-uniformities can be sufficient to cause significant thermal diffusion to set in. Similarly, pressure controls are very important. If you are running the deposition chamber at a particular pressure, you have to maintain the pressure as precisely as possible, because even small excursions in pressure can impact both diffusional velocities as well as inertial effects also. you have to ensure that particles when they leave the orifice are being delivered at a constant velocity, because especially in the case of larger particles, the velocity determines the impact potential to the surface. So, the output from the nozzles should be tightly controlled in such systems in order to ensure that the particles are delivered to the deposition surface in a repeatable and reproducible way. Okay, so the sixth requirement is that in order for you to estimate the prevailing adhesion force, as I mentioned, you can do it in two ways. You can look at individual particles and look at the kinetics of how they get dislodged from the surface, or you can take a set of particles and define a mean adhesion force for this set of particles. In the latter case, what you do is initially you clean the wafer, you deposit a certain number of particles on the surface of known size and count, and then you apply the removal force and you look at what percent of particles are removed. So, when you follow that technique, essentially what you will be doing is this will be your step in the process, and this is percent removal. So, let us say that at time 0 you start with some 100 particles on the surface. You apply your particle removal force one time. It may be something as simple as blowing air. We will talk about particle removal forces in more detail later in this lecture and in the next lecture, but you can imagine that if you are trying to remove a particle from a surface and you want to do it in a, again in a measurable and controllable way, you can just have an air nozzle and blow air across the surface at some velocity. So, let us say that that is your removal step. So, after step 1 you would have removed some particles, and let us say that now you are at 80. You take one more step and now you are at, let us say, 60, and you apply one more adhesion force, now you are at 45 and so on. So, essentially you will follow some curve like this, where a certain number of particles will be removed every time, and this will typically have an asymptotic behavior. Typically when you are trying to remove particles from a surface, the efficiency of removal will be very high in the first stage of extraction, and then it will quickly drop, because the particles that are easy to remove would have been removed in the first stage of extraction or particle removal. The particles that are still left are going to be increasingly difficult to remove. So, you will take something like this, and then what you do is you estimate where this curve intersects at 50% removal efficiency and you calculate the force required to remove 50% of the particles. Now, corresponding to each of these stages of particle removal, you can estimate the amount of force that has been supplied to the surface. So, corresponding to the time that it takes to remove 50% of the particles of a certain size, you can estimate the corresponding force F50. Now, by convention, F50 is taken as a representation of adhesion force. Now, obviously in terms of absolute magnitude, this is not realistic, because when you apply this force you are still leaving 50% of the particles on the surface. So, consider it more like a half-life definition. This is what it takes to remove 50% of the material. The reason that we do not define F100 as the adhesion force is that it might take a long time to get to 100% removal, and it is not practical to wait until you have removed all the particles in order to define a corresponding adhesion force. So, for practical purposes, by convention, by tradition, we take F50 to be a representation of adhesion force. Of course, F50 is very much a function of dP. As we were discussing in earlier lectures, the finer the particle, the more difficult it will be to dislodge it from a surface, even though adhesion force scales as particle size, but we know from empirical evidence that finer particles are more difficult to remove compared to coarser particles. So actually if you take this parameter F50 and you plot that against dP, what kind of curve would you expect? As the particle size gets smaller, the force to remove it becomes larger. In fact, this is a kind of curve you will expect. The force to remove 50% of the particles will increase exponentially as particle size drops. So, a nanometer sized particle compared to, let us say, a millimeter sized particle will be almost infinitely more difficult to remove from a surface. Hence the challenge of particle removal from surfaces. Many of the techniques that we normally use, like wiping or vacuuming or dusting or blowing with air, all of that works well for particles that are in this size range, where it is reasonably easy to remove particles from a surface. But many of these methods will not even be slightly effective when you talk about particles in the nanometer or even micrometer size range. So this is how we characterize adhesion of particles on a surface. Now one of the questions is, how do you estimate this percent removal? What techniques are available for you to do that? Well, we have examined some of these techniques earlier. So for example, optical microscopy, scanning electron microscopy, image capture techniques, laser scanning, some of these techniques work well for single particles and some of them work well for assemblies of particles. For example, an optical microscope is very conveniently used to look at a fairly large surface. For example, if you are looking at particles that are coating this entire substrate and then you wash it with water, right, and you want to know how many particles are still left, how would you do it? Well, you can just look at it if the particles are big enough, but if you want to be able to tell whether even the finer particles have been removed, you will probably take a magnifying glass, right, and just go over the surface. So for a large surface and for coarse particles, an optical microscope would do fine. A scanning electron microscope, on the other hand, would be required if you are looking at how individual particles are getting dislodged from a surface, or if you want to know how particles in the 1 micron size range are getting removed from a surface. So for example, if you again have a semiconductor wafer and you are worried about impurity particles on the wafer and your critical dimensions are of the order of 0.1 microns, then you really need to know how well particles in the 0.1 micron size range are adhering to the surface. So in that case, you will have to use a scanning electron microscope to do the characterization. Image capture and laser scanning we talked about earlier as two essentially alternative techniques to look at particles on a surface. In image capture, it works very well when you are trying to do this experiment on particle adhesion, because essentially you take a surface, you will deposit particles on it, take a photo, right, and that is your reference. Then you apply a certain force to the surface, and after the force has been applied, take another photo or image and then do an image comparison. There are software that can do this automatically for you, and they will quickly tell you, just based on comparison of subsequent images, what percent of particles that were present initially still remain after the cleaning process has been applied. So image analysis, image capture and analysis gives you a very convenient way to characterize particle adhesion. Laser scanning, on the other hand, it certainly improves the sensitivity and the resolution of the method, but it does require that you look at light scattering characteristics from a surface, again before and after application of the cleaning step. So laser scanning works well when you have a highly polished and smooth surface where the surface itself is not going to interfere with your measurements. But it doesn't work so well when you have, for example, a silicon wafer on which you have already put down a pattern, some circuits, some conductive paths, some semiconducting paths, and so on. Because once you have put down these features on the surface, they act as noise in the measurement, and they actually interfere with your ability to measure the signal, which is the particles that have been deposited and removed from the surface. So all these techniques are semi-qualitative because they can also give you a pictorial or visual representation of how particles adhere to a surface and how they are removed from a surface. But they are also quantitative in the sense that they will enable you to count and obtain removal efficiencies. But there are other techniques which are much more conveniently used if you are only interested in doing counting. For example, once you have, let's say that this is your wafer, and on this you have deposited a known number of particles of a known size distribution, and now you want to apply a force to remove the particles, right? Let's say that what you're doing is just taking compressed air and blowing it on the surface, and you're going to look at how many particles are removed when you have blown air for a certain period of time. Now, in order to look at the extraction efficiency, there are two ways in which you can do it. You can look at the surface before and after, or what you can do is the air that comes out after it's passed through over the surface, you can count particles in the air, right? So it's a much more direct measure. So some of these particles would have become airborne, and now they'll be suspended in the air stream. So you can actually compare the count of particles that have become airborne to the count of particles that were on the surface to begin with. Obviously, the ratio between these two is related to the adhesion force. The stronger the force of adhesion, the fewer will be the particles that become airborne for a certain pressure and velocity of air passing over the surface. Alternatively, you can do this with, for example, liquid spray. You can imagine again a surface like this, and you want to know how many particles there are. Instead of trying to measure particles on the surface before and after, you clean it with a liquid and then collect a sample of the liquid and count particles in the liquid. Now, the requirement here is the fluid itself must be pure before you blow it on the surface or you spray the surface with it, because what you are looking at is the delta. How many particles were in the fluid to begin with, and how many particles are there in the fluid after you have used it to remove particles from the surface. But if you have the ability to do that, if you have the ability to supply clean fluid and actually quantify particles that have been entrained into this fluid, then the delta will tell you how many particles have been loosened from the surface and entrained in the fluid, and that would be an indirect measure of the adhesion force of the particle to the surface. Another extension of this, and again we will talk about this in more detail later on, is ultrasonics. As we will discuss later, ultrasound is a way of removing virtually 100% of particles from a surface regardless of their size. Ultrasound is the only mechanism that can remove particles that are as large as a millimeter to particles that are as small as a nanometer. So here again, essentially the way you would do this is take the surface, immerse it in an ultrasonic medium, remove particles from it by turning on the ultrasonics, and then look at particles that have become entrained in the liquid, and that gives you a measure of how strongly they were adhered to the surface to begin with. Okay? So there are many different ways to measure particle adhesion forces to a surface, and you can be as basic and fundamental as you like, or you can be as applied and practical as you like. So, the way that you actually measure particle adhesion force to a surface to a large extent depends on your own application. What are you trying to achieve by measuring the adhesion force? What level of information do you need? Do you need to know how every individual particle sticks to the substrate that you are interested in, or you just want to have a feeling for the overall adhesive nature of the particulate assembly or powder that you are dealing with? So, depending on your needs, you can essentially customize your method of measuring the adhesion force. Now, one of the things that is obviously central to our discussion is the removal force itself, because the going back to this curve where we have plotted the percent removal as a function of removal force, you can imagine that depending on how you apply the force, the results may be very different. For example, the same magnitude of force can be applied by scrubbing the surface with a brush, or by directing pressurized air onto the surface, or by doing sonication. You can tune these so that you get the same magnitude of force. However, what you will find is that the particle removal characteristics are very different in these cases, because they all act differently on particles of various sizes. So, one of the things to keep in mind is this definition of adhesion force by measuring the force required to remove the particles is also dependent on the technique that you use to remove the particles from the surface. So, this F50 that you have estimated as your adhesion force is not a unique number. It will actually depend on the method that you have used to remove the particles from the surface. So, clearly the particle removal method also plays a significant role in determining the adhesion force of the particle to the surface, but also in a practical sense. If you have a critical application in which you cannot tolerate particles on a surface and you have to remove the particles completely, what type of cleaning method do you apply? What particle removal method would you apply? The selection of the particle removal technique depends on many factors. The nature of the surface is very important. For example, if you have a surface that is very delicate, you really cannot apply excessive force to it. So, you have to be very gentle in your cleaning process. On the other hand, if you have a metal and which can withstand fairly high forces, then you can imagine doing high pressure spray cleaning or brushing with metal bristles, or using ultrasonic cleaning. So, these are aggressive cleaning methods to remove particles from surfaces which you cannot apply. For example, if you have a plastic or a rubber or paper, if you are trying to remove dirt from paper, would you be able to spray it with water? No, because it will totally destroy the paper, right. So, you have to match it, you have to match your particle removal method to the substrate from which you are trying to remove the particles. The geometry also becomes important. If you have a flat surface, the way you would remove particles from that would be very different compared to the methods you would come up with to remove particles from more complex surfaces. If you have a lot of hidden features or recesses in the material, then for example, a simple air blow off might not work, because it may remove particles from the flat portions, but it probably would not enter into, let us say you have screw holes. You really cannot remove debris from screw holes just using compressed air. You have to come up with a different technique to be able to do that. So, the material, the physical characteristics, as well as the geometrical features, and of course, the chemical characteristics as well. If you have a substrate that reacts with a certain solvent, then you cannot use that solvent to remove dirt from that surface, right. For example, if you have a material which oxidizes in water, let us say magnesium or aluminum, you cannot clean a magnesium surface using water, because you will immediately form magnesium oxide, which is almost an explosive reaction. Same thing with aluminum. If you run water over aluminum, it will immediately oxidize and form aluminum oxide, and if you don't want that, then you really cannot wash aluminum with water, right. So all these aspects of the substrate have to be taken into account when you are trying to define a method for removing particles from a surface. And similarly, the nature of the contaminant must also be taken into account. Is the contaminant we are trying to remove something that is native to the material, or is it something that is external? For example, again, if you have a metal surface, the metal particles that are left over from when that metal surface was fabricated themselves act as an impurity that you can remove, but that would take a very different process compared to if you are more concerned about removing dust and debris that has collected on this metal surface as an external contaminant or impurity. So depending on the nature of the particle that you are trying to remove, you have to customize your removal method, and this again goes back to the adhesion force. The particles that are native to the metal or material are likely to be more strongly adhered to the surface, because these particles were probably generated during the original manufacturing process of that component, whatever it is, whereas particles that are external, which are deposited, are likely to be looser. I mean, dust, for example, when it accumulates on a surface, it's very easy to clean, right, but if the particle is something that was on the surface to begin with from the time it was molded or machined, then it's very strongly adhered to the surface and it's going to be very difficult to remove. So the particle removal technique that you choose must match not only the substrate from which you are trying to remove the particle, but it must also reflect the nature of the particle that you are trying to remove from the surface. So these are two important considerations. The third important consideration is how clean is clean. You know, when we talk about particle removal from a surface, cleanliness is not an absolute value. I mean, I'm sure you have heard the saying that cleanliness is in the eyes of the beholder, right. A more functional representation of that is to say that a surface must be as clean as it needs to be. You can never achieve 0 particle levels on any surface, because nature is against you. Let us say that you take this surface and you clean it and you clean it, and you actually achieve 0 level of particles down to, let us say, 0.001 nanometers, right. How long is it going to stay that way? Not even for a nanosecond, because as soon as you have completed your cleaning process, nature is constantly depositing more material there. So you will never achieve a perfectly clean or 0 particle substrate. So you have to determine what do you need for your product. You know, if you're making a hard drive, maybe you need to have a surface that's very pristine. On the other hand, if you are supplying chairs to a classroom,